We turn now to the subject of antiderivatives. And for those of you following along in the Thomas textbook, this corresponds to section 4.8. Um, so we define an antiderivative as follows. Let's suppose that capital F prime, let's clarify capital F and lowercase f are different functions. They're not the same. And I'm going to try to make it clear whether I'm writing a capital F or a lowercase f. So let's suppose that there's a function capital F and its derivative, capital F prime, is equal to lowercase f for all x in some interval I. Then we say that capital F is an antiderivative of f of x. So here's an example. Find an antiderivative of f of x equals x squared. So we're just looking for a function whose derivative is x squared. The answer is, and I'll show you the rule for this a little bit later, we would write f of x is equal to 1/3 x cubed. Now, how do we know that this is an antiderivative of lowercase f? Well, we can find its derivative. We can simply say f prime of x is equal to 3 times 1/3 x squared, which is just x squared, and that equals f of x. So it's clear that capital F is in fact an antiderivative of lowercase f. Now, the thing to observe, though, is that I could have chosen a different function. Let's suppose that instead I choose g of x is equal to 1/3 x cubed minus 1017. If I find the derivative of g of x, of capital G of x, I get once again x squared, because apply the same power rule for derivatives to the 1/3 x cubed, and of course the negative 1017 is a constant, so it just becomes 0. So this is also equal to f of x. And I could have done this choosing any by adding or subtracting any constant from 1/3 x cubed. So that brings us to this principle. If a function has any antiderivative, if it has an antiderivative, then it has infinitely many antiderivatives. Because, once again, if f of x is equal to x squared, then some antiderivatives of f would be, we could write 1/3 x cubed. We already saw that. 1/3 x cubed minus 1017. 1/3 x cubed plus e to the 1 million. More commonly, as an example, we'd write 1/3 x cubed plus 1, but you know by now that I don't like common examples. I always like hyperbolic ones. So you can see is I can simply add any constant to the result and get another antiderivative. And since there are infinitely many possible real valued constants, that means that there are infinitely many different antiderivatives. There's no such thing as a function that has only one antiderivative. They all have many, many, many antiderivatives. So we have an expression for this. And the way we write it is we say that if capital F is an antiderivative of lowercase f, then the most general antiderivative of lowercase f is this expression, capital F of x plus c, where that c just represents the idea that we could be adding any real valued constant to what I'll think of as kind of the principal antiderivative. In other words, if I say give me an antiderivative of this function, of course you're normally going to just come up with 1/3 x cubed. And that's what I'm calling the principal antiderivative. That's not a term you'll see in the textbook. So that term principal antiderivative is really just my term, but it refers to what I think of as kind of the meat of the antiderivative, where if I write 1/3 x cubed plus c, this is kind of the main part, and then this is just the part that represents the idea that we could be adding any constant. Now, this is the terminology we use to discuss this concept. Let's see if I can fit this whole thing on the page. So we use the symbol called the integral sign. That's this symbol that you see here. It actually looks a little bit like an S, and it's called the integral sign. And what we do is we put the integral sign in front of a function, and we basically surround this function f of x by the integral sign, and then the expression dx, where this is a differential. You've heard me use that term before. This is the same thing that the same dx that appears in the expression dy dx, and I won't get into right now why that belongs there. But in order to indicate that we want the indefinite integral, we write an integral sign followed by the function, followed by d, followed by a variable name. So this is called the indefinite integral of lowercase f of x, and what it refers to is, what it refers to is the most general antiderivative of lowercase f. In other words, that capital F plus c, where of course capital F is one of the antiderivatives of f of x. So the when we write an indefinite integral like that, we use, sorry, that's not coming out. We use this term integrand to refer to the function. So essentially what this expression means is that we want to find the most general antiderivative of the function f, which we're calling the integrand. And by the way, the name for x is, it's called the variable of integration. So that's the terminology that we use to describe this concept. Basically, if the question is find all the antiderivatives of a particular function, you're going to see it written this way. You'll see an integral sign followed by a function followed by d followed by the variable of integration.